My name is Sargon, Lazar, and I'm going to be talking about the pneumococcal pneumonia vaccine Prevnar 13, which is manufactured by Pfizer. Streptococcus pneumoniae is the main bacteria responsible for otitis media, meningitis, and pneumonia. There is a high morbidity and mortality in both adults and children. Before the Prevnar vaccine was introduced, incidence of invasive pneumococcal disease for children under 2 was 200 cases per 100,000 every year. Prevnar 13 is a 13-valent pneumococcal conjugate vaccine and a successor to Prevnar 7, which is a 7-valent pneumococcal conjugate vaccine that was first released in the year 2000. Prevnar 13 contains 13 distinct polysaccharide protein conjugates. Each conjugate has a capsular polysaccharide from a different serotype of Streptococcus pneumoniae that is also conjugated to a carrier protein. The carrier protein used is CRM197, which is a diphtheria toxoid. The adjuvant is aluminium-based. Aluminium hydroxide, aluminium phosphate, or aluminium sulfate are examples. Each pneumococcal conjugate is prepared separately before being constructed into a single dosage formulation. Generally, there is a 3-step procedure for each polysaccharide protein conjugate. Firstly, fermentation and harvest, followed by purification, before it is dispensed into containers in readiness for shipping. But the specific preparation of each polysaccharide is a little more complicated. The American Culture Collection, or ATCC, provided strain 6301 of S. pneumoniae serotype 1. The strain was expanded and had components of animal origins removed in the process of creating an initial stock to use in the experimentation and production process. Each conjugate has a capsular polysaccharide from a different serotype of Streptococcus pneumoniae that is also conjugated to a carrier protein. Firstly, the capsular polysaccharide is prepared. This begins with fermentation and harvesting, where seed bottles containing a soy-based medium are inoculated using cultures from the cell bank. The bottles are then incubated at 36 degrees Celsius without agitation until a sufficient amount of the organism has developed. Sodium carbonate solution is used to maintain a pH of 7. A seed fermenter containing a soy-based medium is then inoculated using the incubated seed bottles. Once the appropriate optical density, depending on the production target, is reached, the production fermenter that contains a soy-based medium is inoculated with the seed fermenter. Post-cessation of growth finalizes the fermenter's operation, and lysation of the cells is achieved by the addition of sterile 12% deoxycholate sodium that releases the cell-associated polysaccharide. The contents of the fermenter are then allowed to cool before acetic acid is added to adjust the pH of the culture broth to 6.6. A chronological process of clarification of cell lysate using continuous flow centrifugation, depth filtration, and 0.45 micrometer microfiltration is then implemented before purification. Pneumococcal polysaccharide purification involves a series of complex procedures that, unless stated otherwise, are undertaken at room temperature. This includes several concentration/diafiltration operations, precipitation/elution, column chromatography, and depth filtration. The initial step is to use a 100 kilodalton molecular weight cutoff filter to concentrate and diafilter the clarified broth of S. pneumoniae when starting purification. A sodium phosphate buffer at neutral pH is used in this procedure that results in the diafiltration removing medium components of lower molecular weight from higher weight biopolymers like nucleic acids, proteins, and polysaccharides. Precipitation is achieved through the addition of hexaadesyl trimethyl ammonium bromide at 1% Hb concentration, and a depth filter is used to capture the precipitate before the filtrate is discarded. Resolubilization and elution of the polysaccharide precipitate from the depth filter is achieved by recirculating a solution of sodium chloride through the filter. A final rinse of sodium chloride solution of the filters is undertaken to remove any precipitate. Sodium iodide acquired from a stock solution is added to the polysaccharide solution until a final concentration of 0.5% of the precipitate Hb is reached. The solution is then depth filtered once again, which separates the precipitate from the filtrate. The filtrate now contains the desired polysaccharide. The depth filter and precipitation vessel are then rinsed with an NaCl solution, and the rinse is combined with the polysaccharide filtrate. The solution is ready for concentration via another run through a 0.2 micrometer filter. A 30 kilodalton molecular weight cutoff ultrafilter and diafilter with sodium chloride solution further concentrate the solution. Still only partially purified, the polysaccharide solution is filtered through a depth filter containing activated carbon. It is also rinsed with sodium chloride solution, and the rinse is combined with the filtered polysaccharide before being put through another 0.2 micrometer filter. After being placed through another 30 kilodalton molecular weight cutoff ultrafilter, the solution is adjusted with a 1 molar sodium phosphate buffer until a final concentration of 0.025 mole sodium phosphate is reached. At this stage, the pH needs to be checked and adjusted to 7 plus or minus 0.2 if necessary. To obtain correct conductivity, a ceramic hydroxyapatite column is equilibrated with a sodium chloride containing sodium phosphate buffer before the polysaccharide solution is loaded onto the column. This removes any remaining impurities via a flow-through column. The 0.2 micrometer inline filter situated before and after the column also enhance the purity of the polysaccharide, before filtering through another 30 kilodalton molecular weight cutoff filter and water for injection via filtering tool took place. A filtration through a 0.2 membrane filter and into a set of polypropylene bottles is the final purification step. The bottles are then frozen and stored at minus 25 degrees to minus 5 degrees Celsius. Characterization of the correct compound is confirmed through NMR spectroscopy with HNMR. Preparation of serotype 1 pneumococcal saccharide CRM conjugate first starts with activation and conjugation. A reaction vessel, which is used to thaw and combine a purified polysaccharide solution before 0.2 molar of sodium carbonate and pH 9 were added and incubated for 3 hours at 50 degrees. Once the vessel was cooled to 20 degrees Celsius, 0.2 molar acetic acid is added to achieve neutralization. Solution is oxidized whilst in the presence of sodium periodate at 2 to 8 degrees Celsius and stirred for 15 to 21 hours. 0.9% sodium chloride and a 30 kilodalton molecular weight cut-off membrane is used to concentrate and biofilter the solution 10 times over, and the retentate is then put through a 0.2 micrometer filter. The activated saccharide is then filled into 100 ml lyophilization bottles, shell frozen at minus 75 degrees and lyophilized. Lyophilization refers to a freeze-drying method that utilizes a motorized technology to rotate the bottles in an appropriate medium such as alcohol, which forms an interior surface inside the bottles. This is ideal for freeze-drying. The CRM197 solution at a saccharide-protein ratio of 2 to 1 is then used to resuspend the lyophilized material after it has been brought back down to room temperature. 1 molar sodium phosphate buffer is added to a final ionic strength of 0.2 mol and a pH of 7.5. Sodium cyanoborohydride is then added and the reaction mixture is incubated at 23 degrees for 18 hours, followed by a secondary incubation period of 72 hours at 37 degrees Celsius. Once the incubation period is complete, the reaction mixture is diluted in cold saline, and the pH is adjusted to 9 through the addition of 1 molar sodium carbonate. To quench unreacted aldehydes, sodium borohydride is added and the mixture is incubated between 3 to 6 hours at 23 degrees Celsius. A twofold dilution using saline is performed before the mixture is transferred through a 0.45 micrometer pre-filter and into a retentate vessel. It is then biofiltered 30 times with 0.15 mol phosphate buffer at a pH of 6.8 and then again 20 times with saline. The mixture is concentrated further using a 0.2 micrometer filter. The conjugated solution goes through a final dilution of 0.5 milligrams per milliliter in 0.9% saline solution and is then sterile filtered into final bulk concentration containers using a Class 100 hood. It is stored between 2 to 8 degrees Celsius. This process takes place for all 13 serotypes and conjugates. Formulation of the multivalent pneumococcal conjugate vaccine starts initially when the required amount of final bulk concentrate is calculated based on the batch volume to be processed. 5 millimoles sodium succinate buffer at 5.8 pH is added to types 3, 6A, 7F, and 19A before final bulk concentrates are added. A millipore Durapore membrane filter unit is then used to sterile filter the final solution into a second container. A gentle mixture is then implemented before, during, and after the addition of aluminium phosphate. After the final mixture, the formulated bulk product is stored between 2 to 8 degrees Celsius. The packaging of the product is accomplished by filling type 1 borosilicate glass syringes at 0.5 milliliters with the final solution made possible by Becton-Dixon syringes. The filled vaccine, final product, is then stored at 2 to 8 degrees Celsius until shipping. Thank you for listening, and I hope you enjoyed my presentation on Prevnar 13. Thank you.